OSPF, Open Shortest Path First. OSPF is perhaps the most popular link state routing protocol. It is an open standard, so it can run on routers produced by different vendors, which is in contrast to EIGRP, a Cisco proprietary protocol that can only run on Cisco devices. OSPF is classless and supports features such as VLSM, manual route summarization, incremental updates, equal cost load balancing, etc. As the metric, OSPF uses a single parameter, that is the interface cost. OSPF uses the multicast address of 224.0.0.5 and 224.0.0.6 for the communication between OSPF enabled routers. The default administrative distance for OSPF router is 110. Routers running OSPF need to establish neighbor relationship before exchanging routing updates. Since OSPF is a link state routing protocol, neighbors don't exchange routing table, instead they exchange information about network topology. Each OSPF router then runs the SFP algorithm to calculate the best routes and adds those to the routing table. OSPF router stores routing and topology information in three tables. The neighbor table. This table stores information about OSPF neighbor. The topology table stores the topology structure of the network, and the routing table stores the best route for the network. OSPF neighbor discovery. Routers running OSPF need to establish a neighbor relationship before exchanging routing updates. OSPF neighbors are dynamically discovered by sending hello packets out each OSPF enabled interface on a router. Hello packets are sent to the multicast IP address of 224.0.0.5. If two neighbors have compatible OSPF parameters listed in the hello packets, the neighbor relationship will be formed. By default, hello packets are sent out every 10 seconds on an Ethernet network. A dead interval is 4 times the value of the hello interval. So if a router on an Ethernet network doesn't receive at least one hello packet from an OSPF neighbor for 40 seconds, the router will declare the neighbor to be down. The following field in the OSPF hello packet must be same on both router in order for the routers to become neighbors: subnet, area ID, hello and dead interval timer, authentication, area stub flag, and MTU. The neighbor discovery process is explained in the following example. Routers R1 and R2 are directly connected to run OSPF. Both routers will start sending hellos to each other in order to establish a neighbor relationship. If the routers have compatible OSPF parameters, the neighbor relationship will be formed. Each OSPF router is assigned a router ID. A router ID is determined by using one of the following methods: using router ID command under the OSPF process, using the highest IP of the router's loopback interface, and finally using the highest IP address of the router's physical interface. OSPF neighbor states. Before establishing a neighbor relationship, OSPF routers go through several state changes. The first one is down state. No hellos have been received on the interface. All OSPF routers begin in this state. Second is the attempt state. Neighbors must be manually configured. This state is used only in non-broadcast multi-access networks. Init state. A router has received a hello message from the other OSPF router, but the two-way conversation has not yet been established. Two-way state. The neighbor has received the hello message and replied with a hello message of his own. Xstart state. Beginning of the link state database exchange between both routers. Routers will start to exchanging link state information. Sixth is the exchange state. Database descriptors, that is DBD, packets are exchanged. DBDs contains LSA header. Routers will use this information to see what LSA needs to be exchanged. LSA stands for link state advertisement. Loading state. One neighbor sends out LSR, that is link state request, for every network it doesn't know about. The other neighbor replies with LSU, that is link state update, which contains information about requested network. After all the requested information have been received, other neighbor goes through the same process. The final is the full state. Both routers have synchronized the link state database and are fully adjacent with each other. OSPF routing can now begin. OSPF area concept. OSPF uses areas to simplify administration and optimize traffic and resource utilization. An area is simply a logical grouping of contiguous network and router. All routers in the same area have the same topology table and don't know about routers in the other area. The main benefits of using an area is OSPF networks are the routing tables on the routers are reduced, less time is required to run the SFP algorithm since routers need to recalculate their link state database only when there is a topology change within the area. Routing updates are reduced. Each area in OSPF network must be connected to the backbone area, also known as area 0. All routers inside an area must have the same area ID in order to become OSPF neighbor. A router that has interface in more than one area, area 0 and area 1, is known as area border router. A router that connects an OSPF network to other routing domain to an EIGRP network, for example, is called as Autonomous System Border Router, that is ASBR. Consider the following example to better understand the concept of areas. All routers pictured are running OSPF. You can see that one router is an ABR, that is area border router, because it has interfaces in two areas, namely area 0 and area 1. One router is an ASBR, that is autonomous system border router, because it connects the OSPF networks to another routing domain, an EIGRP domain in this case. The role of an area border router is to forward routing information from one area to the other. The role of an ASBR is to connect an OSPF routing domain to another external network, example Internet, EIGRP network, etc. The manual route summarization is possible only on ABR and ASBR. Link State Advertisement or LSA. The LSAs are used by routers running OSPF to exchange topology information. An LSA contains routing and topology information that describe a part of an OSPF network. Routers exchange LSA and learn the complete topology of the network until all routers have the same topology database. When two neighbors decide to exchange routes, they send each other a list of all LSA in their respective topology database. Each router then checks its own topology database and sends a link state request, that is LSR, requesting all LSAs not found in its topology table. The other router responds with link state update, that is LSU, that contains all LSAs requested by the neighbor. To better understand how LSAs are used in OSPF, consider the following example. In the example, we have two routers and a single computer. After configuring OSPF on both routers, routers exchange LSA to describe their respective topology database. Router R1 sends an LSA header for its directly connected subnet, that is 10.0.0.0/24. Router R2 checks its topology database and determines that it doesn't have information about that network. Router R2 then sends link state request message requesting further information about their subnet. Router R1 responds with its link state update, which contains information about subnet 10.0.0.24, such as next hop address, cost, etc. Types of LSA. There are several different LSA types in OSPF. Type 1 LSA, also known as Router Link Advertisement or RLA. A Type 1 LSA is sent by every router to other routers in its area. It contains the router ID, interfaces, IP information, and current interface state. Type 1 LSAs are flooded only across their own area. Type 2 LSA, also known as Network Link Advertisement or NLA. A Type 2 LSA is generated by designated routers to send out information about the state of other routers that are part of the same network. Type 2 LSA are flooded across their own area only. Type 3 LSA, also known as Summary Link Advertisement or SLA. A Type 3 LSA is generated by area border router and sent towards the area external to the one where they were generated. It contains the IP information and router ID of the area border router that is advertising a Type 3 LSA. Type 4 LSA informs the rest of the OSPF domain how to get to the autonomous system border router. The link state ID includes the router ID of the described ASBR. Type 5 LSA, also known as AS External Link Advertisement. Type 5 LSA is sent by ASBR to advertise routes that are external to the OSPF autonomous system and are flooded everywhere. Now let us go ahead and configure OSPF. In the given example, all the devices come under single area, that is area 0. No IP configuration has been done on any of the devices. The end devices are connected to a switch, which in turn are connected to two routers. We'll go ahead and configure IP on the end devices first. For PC0 and PC1, the default gateway is gigabit 0/0/0 of router R0. So we'll go ahead and configure the PC0. Desktop IP configuration 10.0.0.1 with default subnet mask, and gateway is 10.0.0.3. Similarly for PC1, IP address is 10.0.0.2 with default subnet mask, and gateway is 10.0.0.3. Now for PC2 and PC3, the default gateway is 192.168.0.3, which is gigabit 0/0/0 of router R1. Go to PC2, desktop, IP configuration, IP address is 192.168.0.1 with default subnet mask, and gateway is 192.168.0.3. Similarly for PC3, 192.168.0.2 with default subnet mask, and gateway is 192.168.0.3. So we have now configured IP addresses on all end devices. We'll now go ahead and configure IP addresses on both the routers. Now router 0 has two interfaces, gigabit 0/0/0 and 0/1. So we'll go into router 0, CLI, no, to enable mode, then configuration mode. First interface that we will configure is interface gigabit 0/0/0 interface. IP address is 10.0.0.3 with default subnet mask, and no shut to bring up the interface. Now the other interface, that is interface gigabit 0/0/1, IP address is 172.16.0.1 with default subnet mask, and no shut command to bring up the interface. Similarly for router R1, no, enable mode, configuration mode, interface gigabit 0/0/0, IP address of 192.168.0.3 with default subnet mask, and no shut command to bring up the interface. Similarly for interface gigabit, the WAN side is 0/0/1, IP address 172.16.0.2 with default subnet mask, and no shut command to bring up the interface. As of now, we have configured IP addresses on all the interfaces. Now if you try to ping from PC0 to PC2, it won't go because we have not configured any routing protocol on these routers. From PC0, if you try to ping PC2, that is 192.168.0.1, we get the result as destination host unreachable. So let's go ahead and configure OSPF on both the router. The command for configuring OSPF is router OSPF One is the process ID. Process ID can range from 1 to 65,535. Now router 0 is part of two network, the 10 network and 172 network. So we'll specify network 10.0.0.0, and here we'll give the wildcard mask and not the subnet mask, that is 0.255.255.255 and area 0. Similarly, network 172.16.0.0 and the wildcard mask, that is 0.0.255.255 and area 0. Do right to save the configuration and exit. Similarly for router 1, now router 1 is part of two networks, the 192 network and 172 network. So router 1, router OSPF 1, network 192.168.0.0 and the wildcard mask is 0.0.0.255, area 0. Similarly, network 172.16.0.0, 0.0.255.255 is the wildcard mask and area 0. Do right to save the configuration and exit. Now let's go ahead and try to ping PC2 from PC0. Earlier we got destination host unreachable because we did not configure any routing protocols. Now OSPF has been configured. So let's go ahead and try to ping. The first packet will be dropped because the routers are trying to build the ARP cache and we are getting a response back from 192. Now if we try to ping again, we won't get the request timeout. Yeah. So this is how OSPF is configured in a single area network. Now let us go and configure multi-area in OSPF. In the given example, router R1 and R2 belong to area 0, while R0 belongs to area 1 and R3 belongs to area 2. No IP configuration has been done on any of the devices. So we'll go ahead and configure IP addresses. For the PC0 and PC1, the default gateway is 10.0.0.3 of gigabit 0/0/0 of router R0. PC0 10.0.0.1 with default subnet mask and gateway is 10.0.0.3. Similarly for PC1, 10.0.0.2 with default subnet mask and gateway is 10.0.0.3. Now for PC2 and PC3, the default gateway is gigabit 0/0/0 of router R1. So for PC2, 192.168.0.1 with default subnet mask and gateway is .3. Similarly for PC3, 192.168.0.2 with default subnet mask and gateway is .3. And for PC4 and PC5, the default gateway is 172.16.0.3, which is gigabit 0/0/0 of router R3. So go to PC4, 172.16.0.1 with default subnet mask and gateway is 172.16.0.3. Similarly for PC5, 172.16.0.2 with default subnet mask and gateway is .3. Now we have configured IP addresses on all end devices. We'll go ahead and configure IP addresses on router. For router 0, there are two interfaces, gigabit 0/0/0 and 0/0/1. To enable mode, configuration mode. First interface is interface gigabit 0/0/0, IP address 10.0.0.3 with default subnet mask, and no shut command to bring up the interface. The other interface is interface gigabit 0/0/1, IP address is 20.0.0.1 with default subnet mask, and no shut to bring up the interface. I will go to router 1. Router 1 has 3 interfaces. We'll go for no, enable mode, configuration mode. First interface we'll take as gigabit 0/0/0. IP address is 192.168.0.3 with default subnet mask, and no shut to bring up the interface. Next interface we'll take as interface gigabit 0/0/1. IP address is 20.0.0.2 with default subnet mask, and no shut to bring up the interface. And the last interface, that is interface gigabit 0/0/2, IP address of 30.0.0.1 with default subnet mask, and no shut to bring up this interface as well. Now we'll go to router R2. R2 has 3 interfaces, but we are using only 2 interfaces. So we'll go to R2. Nope. Enable mode, configuration mode, then interface gigabit 0/0/2, IP address of 30.0.0.2 with default subnet mask, no shut to bring up the interface. The other interface is interface gigabit 0/0/1, IP address of 40.0.0.1 with default subnet mask, and no shut to bring up this interface as well. Now the final router R3 has 2 interfaces that are in use. R3 CLI. No, get into enable mode, configuration mode, interface gigabit 0/0/0, IP address of 172.16.0.3 with default subnet mask, and no shut to bring up this interface. Similarly, interface gigabit 0/0/1, IP address of 40.0.0.2 with default subnet mask, and no shut to bring up this interface. Now we have configured IP addresses on all the devices, on all routers and all the end devices. As of now, no routing protocol has been enabled on these routers. Now if you try to ping from PC0 to PC4, we'll get the response as request timeout or destination host unreachable. So ping PC4 is 172.16.0.1. We're getting response as destination host unreachable because no routing protocol has been configured on any of this router. So let's go ahead and configure OSPF. For router 0 is part of area 1. We'll go ahead and configure router 0 as area 1. So the command is router OSPF 1, where 1 is the process ID, network. Now router 0 is part of 2 network, the 10 network and 20 network. Network 10.0.0.0 with the wildcard mask that is 0.255.255.255 and area 1. Similarly, network 20.0.0.0 with default wildcard mask that is 255.255.255 and area 1. Do right to save the configuration and exit. Now let us configure OSPF on router R3. R3 is part of area 2. So we'll go to R3, router OSPF 1. Now R3 is part of two networks, the 40 network and 172.16 network. So network 172.16.0.0 with the wildcard mask that is 0.0.255.255 area 2. Similarly, network 40.0.0.0 wildcard mask of 0.255.255.255 area 2 and do right to save the configuration. Now we will configure router R1. Now R1 is an area border router. It has one interface in area 1 and the other interface in area 0. So we'll go ahead and configure router R1. Router OSPF 1 network 20.0.0.0 with default subnet with default gateway, and this is in area 1. The interface gigabit 0/0/1 of router R1 is in area 1. In network 192.168.0.0 with the wildcard mask of 0.0.0.255. This is in area 0. And the last network, that is network 30.0.0.0 0.255.255.255 area 0, and do right to save the configuration. Here we can see that as soon as we entered 192.168, we've got a OSPF agency formed. Similarly, for router R2 is also an area border router because it is one of its interface is in area 0, the other interface is in area 1. Go for router R2. Router OSPF 1 network 40.0.0.0 with default wildcard mask. This is in area 2. And the other network is in area 0, that is 30 network. So we'll go ahead and type it out. Network 30.0.0.0 with default wildcard mask, area 0, and do right to save the configuration. Here also we can see that the neighborship has been established. You can see loading done. Now let's go ahead and try to ping from PC 0 to PC 4 and see if we can establish neighborship. We have pinged PC 4. The first packet is dropped because the routers are creating their ARP cache, and we can see successful neighborship. Let's try to ping from PC 5 to PC 3. It is ping 192.168.0.2. And we are getting a good response back. Try again and we won't get the request timeout. This is how we configure multi-area in OSPF. Here router R1 and router R2 are area border routers who has interfaces in both the areas. Designated router DR and backup designated router BDR. Based on the network type, OSPF router can elect one router to be designated router and one router to be backup designated router. For example, on multi-access broadcast networks such as a LAN, routers defaults to elect a DR and BDR. DR and BDR are elected to minimize the number of agencies formed and to serve as the central point for exchanging OSPF routing information. However, on point-to-point links, the DR and BDR are not elected since only two routers are directly connected. Each non-DR and non-BDR will exchange routing information only with DR and BDR instead of exchanging updates with every router on the network segment. DR will then distribute topology information to every other router inside the same area. The backup designated router, that is BDR, serves as a hot standby for DR. It receives all routing updates from OSPF routers, but it will not disperse LSA updates. To send routing information to a DR or BDR, the multicast address of 224.0.0.6 is used. A DR sends routing updates to the multicast address of 224.0.0.5. If the DR fails, the BDR will take its role of redistributing routing information. On LAN, DR and BDR have to be elected. Two rules are used to elect a DR and BDR. The first one is the router with the highest OSPF priority will become a DR. By default, all routers have a priority of 1. If there is a tie, the router with the highest router ID wins the election. The router with the second highest OSPF priority or router ID will become a BDR. Consider the following example. All routers in the network are running OSPF and are in the same area, that is area 0. Let's say that router R1 and R2 have been elected as DR and BDR because they have the highest and the second highest router ID. If the R4's directly connected subnet fails, R3 informs only R1 and R2 of the network change. R1 then informs all other non-DR and non-BDR routers of the change in the topology. We can verify that R1 and R2 are indeed DR and BDR of this segment by typing the show IP OSPF neighbors command on router R3.